So we're going to start today with looking at how well the line is going to fit the data. So last time we were looking at the least squares regression line itself and making predictions and interpreting slope, and we looked at residuals as well. Remember, residuals were basically how far off our guess was, and so our prediction was, excuse me. So what we have here on the left, this graph here is our residual plot for that truck data that we've been looking at, the miles driven versus the cost of the truck. So these are residuals. So again, these are the differences between the actual cost of the truck and the predicted cost of the truck. And so you'll see everything on the top here. This is a positive residual, meaning that the truck costs more than predicted. And the ones on the bottom here, these are negative residuals, meaning the truck costs less than what was predicted. Well, one of the tools that we can use to see how well our line is going to fit our data, so again, seeing how good this least squares regression line would be, okay, is we can look at the standard deviation of the residuals. Okay, so when we look at the standard deviation of the residuals, that gives us basically the size of our typical error. Remember, it's the same as when we do standard deviation for any other data set, and we talk about the mean, and then we talk about the standard deviation of that data set, and we say that that's the typical distance away from the mean. Well, this is the same thing. This is just the typical residual distance away from the mean. So away from the typical, this is just our typical prediction error. So we've got our formula here for calculating standard deviation of the residuals. We will be doing this in our calculator, or it will be given to us. More often in the beginning here, it will be given to us, and we won't really worry about having to calculate it until later on. Also, just like standard deviation before, our units here are going to be the same. So for instance, our units here for our residuals are dollars, right? The cost and how far off that cost is from the predicted cost, the actual cost and the predicted cost. So our units for standard deviation here would also be dollars, just like it was before. Remember, our units won't change. They're the same. Another tool that we can use to see how good our data fits with our line is the coefficient of determination. Okay, so down here, this r squared. Okay, so the coefficient of determination, or r squared, this is basically how much variation is accounted for with our line. So your official definition here, the fraction of the variation in the values of y, that's accounted for by the least squares regression line of y on x. Basically, the higher your r squared value is, the better your line is. Okay? It gives you the amount of variation that's accounted for by the linear model. So if a lot of the variation is accounted for by the linear model, then we've got a really good model here. If the r squared is really low, then not much of our variation is accounted for here, so our model is maybe not quite as strong. So let's look at both of these in an example with context, and I think that will help. So let's go back to our football example that we've been looking at with the SEC points and the wins. Okay, so the relationship between the average number of points scored per game and the number of wins for the 12 college football teams in the Southeastern Conference. The scatter plot with the least squares regression line is right here. So here's our scatter plot with our least squares regression line. And then here's our residual plot over here. Let's see if I can scoot this over just a smidge so you can see all of it. There we go. Okay, and so what was given us to here is the equation of the line. So here's the equation of our line right here, y hat. So our predicted y equals negative 3.75. That's my y-intercept. Plus 0.437, that's my slope, times x. It also gives me the standard deviation of that of the line, as well as the r squared for the line. So part A here wants us to calculate and interpret the residual for South Carolina, which scored 30.1 points per game and had 11 wins. So this should be the South Carolina point right here. Okay, so let's go ahead and just do part A. So the predicted amount of wins for South Carolina, I just need to plug that information in. Okay, so I can plug in my x here. So there's my points. and their predicted amount of wins was 9.4 wins. So if I want to calculate now my residual for South Carolina, because that's what officially I'm doing here. So to calculate my residual, I need my actual and I need my predicted, right? Remember, they go in alphabetical order, right? My actual minus my predicted. So 11 minus 9.4. So South Carolina has a residual of 1.6 wins. So what that means, because that's my interpretation part, that's the part we're seeming to struggle with a little bit. What that means is that South Carolina won 1.6 more games than expected. We know it was more because it's a positive value based on the number of points they scored per game. Okay, so again, we have to put that context in there. Part B is a linear model appropriate for these data explained. So remember, if I want to see if a linear model is appropriate, I need to look at this residual plot over here. So looking at this residual plot, basically what I'm looking for is a pattern. Is it kind of all over the place without a pattern, or does it have a distinct pattern? This one does not appear to have any kind of obvious pattern, which makes a linear model appropriate. Okay? If there was a pattern, remember if it went like this, or went like this, or went up and curved like that, any kind of obvious pattern, then the linear model would not be appropriate. Part C has us interpreting the value of S. So S is 1.24. Okay, so when I want to interpret it, again, I have to have my context. So when using the least squares regression line, and I explain my line, I have to define my line. So when I'm using that least squares regression line with X equals points per game to predict and Y equals the number of wins, we will typically be off by about 1.24 wins. Okay, this is my typical, basically my typical residual value, right? It's going to be 1.24 wins. And then part D has us interpreting the value of R squared. Well, R squared was given to us as 0.88. So putting that in percent, about 88% of the variation in wins is accounted for by the linear model. And then I have to do the context part, right? Y to X, relating wins to points per game. So that's all my interpretation is. And again, we'll be putting these on our sentence stem chart. So what if you're given this computer summary data? Because you're gonna see it. You're gonna see it on unit tests. You're gonna see it on your AP tests. It shows up in free response prompts. These are the two most common forms. So there's one on each side here. So you see what's called mini-tab data, and this is our JMP data. Again, these are the two most common forms that you see for computer output. If you can interpret one, though, you usually can interpret all of the others. You just have to kind of get a feel for what's going on here. Okay, so when we look at the mini-tab data, so we're looking at mini-tab data only, okay, we've got our y-intercept, which is here in this constant row, right here. Okay, this 38,257. So I've got my y-intercept is there. My slope is this negative 0.16. Okay, the coefficient in the miles driven. It tells me my R squared. R squared is basically just written out right there. It tells me my standard deviation of the residuals. So even though it's just an S, you need to realize that that's the standard deviation of the residuals. Okay, the rest of it you shouldn't really need or use. If you're looking at the JMP computer printout over here on the right, you've got your R square, again, written out for you. Okay, so here's our R square right here. You've got your standard deviation of the residuals, root mean square error. If you look at the formula for it, that name would make sense. But that's our standard deviation of the residuals. Okay, and then down at the bottom, this one is given to you. Here's my intercept right here. And then below it is going to be my slope. So you need to take a look at this information. You'll see you've got standard error here. That's not the same as standard deviation. Okay, so take a look at this and kind of memorize where these things are on these printouts of data. Okay, so let's look at this example using this computer-generated data. So a random sample of 15 high school students was selected from the U.S. Census at School database. The foot length in centimeters and height in centimeters of each student in the sample were recorded. Least squares regression was performed on the data. A scatter plot with the regression line added, a residual plot, and some computer output from the regression are shown below. What is the equation of the least squares regression line that describes the relationship between foot length and height? Define any variables that you use. What that means is you need to define your x and your y. So instead of just writing y hat, right? Instead of just writing y hat, we would go ahead and we would define that. So our predicted height, you can write it like this, because remember the hat means it's predicted. So the predicted height, and then we need our y-intercept on this one. Remember the y-intercept is our constant. So 103.41 plus the slope. Slope was right below it. Okay, so this one right here is our slope, the 2.7, plus the 2.7469. And then again, I need to define my x, so that would be foot length. That was in a parentheses. Okay, so let's see if I can fit this all in one place. So height equals 103.41 plus 2.7469 times foot length. There you go. So that's what your line would look like, and that's what it would look like with you defining the variables. You could also just write, you could write this, you could write x, but then you need a separate sentence that says what y and x are. Okay, interpret the slope of the regression in context. So if you're going to interpret the slope of the regression in context, again, this is a sentence stem that hopefully we have on our chart by now. Okay, so let's look at what that will be. Right, our slope is our change in y for every one change in x. Okay, so x is foot length. So for each additional centimeter of foot length, for each additional centimeter of foot length, that's my 1x here, the least squares regression line predicts an increase of 2.7469 centimeters in height. So for each additional centimeter of foot length, the least squares regression line predicts an increase of 2.7469 centimeters in height. Okay? And we know it's an increase because it's a positive slope. So I am defining, again, both my x and my y as I interpret that slope. Part C asks to find the correlation. You can actually calculate the correlation here because you're given r squared. You don't have to put anything in your calculator or anything like that, right? My correlation is going to be the square root of that. So 0.486 square root of that. Okay. Looking at the data, we know, what we don't know is if this is a positive or negative. But when I look at my scatter plot over here, I can see that it is a positive association. So I know that R is 0.697, not negative 0.697. Okay, and then part D is align an appropriate model to use for this data and explain how you know. So let's go over here and look at our residual plot. Okay, we're looking at, well, we can look at both of them. The residual plot doesn't really show any pattern. Our scatter plot shows a linear association. And so, therefore, you could use both of those to support that this is an appropriate model. Both that the scatter plot shows a linear association and the residual plot does not show any particular pattern. Now, if you had to, you could calculate your least squares regression line with your, without plugging everything into your calculator. You would do that using these two formulas for slope and then for y-intercept. So for both of these, you would need to calculate the mean for the x values and the mean for the y values. And then you would also need to calculate the mean, the standard deviation for the x values and the standard deviation for the y values, as well as their correlation for r. So you can see here's your slope formula here. Again, our formula looks a little bit different here. than it does on your formula chart, because on your formula chart they use the B1, they use the subscripts. We'll look at what it is on your formula chart compared to what it is here. Okay, and then this is how you would calculate your y-intercept. As a whole, again though, this is something that I would say that you would be doing on your calculator. Okay, so looking at our example here. In the previous example, we used data from a random sample of 15 high school students to investigate the relationship between foot length in centimeters and height in centimeters. The mean and standard deviation of the foot lengths are mean of 24.76, standard deviation of 2.71 centimeters. Mean and standard deviation of the height is 171.43 centimeters and 10.69 centimeters for a standard deviation. The correlation between foot length and height is R equals 0.697. So if I'm given all that information, I could just plug it in. If I wasn't given all of that information, if you were actually given the data set, I can't see any reason why you would do this by hand. Really, the only reason you would use this is if this is what you were given. So if this is what you were given, okay, I can calculate slope right here, right? I can take my two standard deviations and I can divide those and multiply by my correlation here, and I can calculate slope. Okay, and then I can calculate the y-intercept by taking the mean of y minus the slope times the mean of x, and I can calculate my y-intercept here, and then I can come up with my final equation for my line. Okay, let's look at one big kind of final example here. I'm not going to write all of it down because there's just not really room. So let's look at the example. Does the age at which a child begins to talk predict a later score on a test of mental ability? A study of the development of young children recorded the age in months at which each of 21 children spoke their first word and their Gesell adaptive score. The result of an aptitude test taken much later. The data appear in the table below, along with the scatter plot, residual plot, and the computer output. Should we use a linear model to predict a child's Gesell score from his or her age at first word? If so, how accurate will your predictions be? So what we're trying to determine here is if a linear model is appropriate for this data. And if so, how good is it? So the first thing we need to do when we're determining if a linear plot is any good, right? So let's look at our scatter plot. Do we see an association that is linear or nonlinear? And we can also look at that residual plot to see if there is no pattern there. So looking at my scatter plot here, I've got a moderately strong here, negative linear association here. There's a couple potential outliers, like this person way out there. Okay, this person that's kind of way away from everybody there. The residual plot doesn't seem to have any particular pattern there. You can also look at, we can look at the computer data then to look for our R-squared, our coefficient of determination, as well as our standard deviation to see how good our model would be. So yes, a linear model would be appropriate. So a linear model would be appropriate for this data, but they might not be very accurate. Let's come up here and look at our standard deviation and our R-squared. So our standard deviation here is 11.0229. Remember, this is the standard deviation of the residuals. So the typical prediction is going to be off by 11.0229 points. And then our R-squared is how much of our variation is accounted for with that model. So only 41% of the variation is accounted for in that model. Over half the scores, over half of the variation in these Gesell scores, these final test scores, they are not accounted for. So even though we could use a linear model, it may not be the best model for this particular data set. So let's look at one last thing here. Let's look at these outliers and influential observations. An outlier is going to be our observation that lies way outside the overall pattern. Points that are outliers in the y direction, so in the up and down direction, but not the x direction of the scatter plot. Those have really large residuals. So, I'm sorry, guys. Points that are outliers, like really high in the y direction, those have really big residuals, not necessarily in the x direction. An observation is going to be influential is if you removed it, would that markedly change the results from my calculations? They're more influential when you have outliers in the X direction than in the Y direction. So, like for instance, if you look down here, you've got a whole bunch of lines here. So we have our initial line, which is that like turquoise color there. Okay, and then they removed child 18, and you can see how it shifted. Child 18 is the one that had the really, that had the pretty low score, and where their age was. And then you can remove, you can see the orange line when they removed child 19 that had a really high score, but their age. You can see how much it shifted when the outlier was at the influential point was in the X direction, where the big difference was in the X direction, versus the amount of shift when it was in the Y direction. Okay, and one last reminder, do not forget that association does not imply causation. Okay, just because you see an association between the data does not imply causation. So be careful when you're writing about these things that you're not saying necessarily that one is causing the other. Okay, so that's it for chapter 3, and we'll practice some of this stuff in class.